Hi, this is the Uni-T UTG9504T Arbitrary Function Waveform Generator, and well, it's a pretty cool bit of kit. But the interesting bit about this is that it's over 5,000 US dollars for this bad boy. And it's from Uni-T, a company famous for making, low-cost test gear. So why does this thing cost 5,000 US dollars or more than that? Well, that's an interesting question. So rather than a normal teardown of this thing, which I guess would be interesting in its own right, I thought we'd actually tear it down and actually have a look and go through at a crude level the BOM cost for this thing and find out why a product like this actually, how it can cost 5,000 US dollars. Might be interesting. Now, I've done an interesting whiteboard video on the economics of selling hardware, and I'll link that in if you haven't seen it. It's very interesting, but basically it comes down to that to economically sell hardware and make a profit, you've pretty much got to at least have a sort of like 2.4, 2.5 times the BOM cost multiple. But for a test equipment company like this, and specifically for a product like this, that's a higher end product. Why does it cost $5,000? The key to why it costs so much is because this is a 500 megahertz bandwidth. 2 gig samples, 2.5 gig samples per second. In fact, there's another model of this one which goes to 600 megahertz. And pretty much the only other function generator on the market that can go to that sort of frequency is a Siglent model, and it costs basically a similar price. I think it's slightly cheaper because it's a smaller user and doesn't have like a huge big touchscreen like this thing does. But so taking that into account, they're basically the same price unit. There's basically nothing else available from any of the mainstream manufacturers. There are a few other niche, like really high frequency function generators on the market, but if you have to ask the price of those, trust me, you can't afford it. So this looks absolutely dirt cheap in comparison. So at a basic level, if you take that like 2.5 times multiplier minimum of BOM cost to a saleable product, and it's going to be higher than that for a product like this, but let's just take that at a 5,000 US dollar price, even though it's a bit more than that, you're still looking at $2,000 in BOM cost. Is there 2,000 bucks worth of parts inside this thing? Well, probably not, but is there $1,000 worth? Is it 500 bucks? How much margin are they potentially making on this? We can't get an exact answer, but let's do a teardown and see if we can have a look and add some things up and, make a few basic assumptions and see if we can come up with a BOM cost for something like this and why it's so expensive. Oh, yes, please. Beautiful. And we've got pretty basic folded metal construction here with your BNC screwed into the back terminals. Oops, a couple of ribbony cables. Let me get those out. Got a little coax jobby. And we're in. And here's our main board. I will take high-res photos of this. All my high-res teardown photos are available on the EEVblog Flickr account, which is linked in on EEVblog.com, so check that out. And yeah, we've got one major part here. Is that a big Xilinx Zinc or something like that? I assume it's an ARM processor for doing all the GUI and OS stuff, surrounded maybe by some FPGA fabric. These here could be your DACs, even though it's a 4-channel unit. We've got 3 parts, although this thing, you don't get the full bandwidth on all 4 channels. It's only available on 2 channels, so maybe the channels 3 and 4. We should be able to get the heatsink off those to check it out. We've got some nice cans here, and then we've got some nice relays here. I'm liking the look of this. So yeah, it's very neat construction. The DC to DC converter up here is, look at this, multi-stage filter in here. Oh, it's a Bobby Dazzler. You don't usually see something like that. It's remarkable. Oh, no, I could be wrong. That could be the application processor down there because it's not doing a lot. It's just, doing some basic GUI level stuff, and then the rest of it's handled by, I presume that's a big FPGA under there. But anyway, we'll take a look at the parts, and it looks like the entire OS is stored on an SD card there. That's just very nice from a developmental point of view. It just makes development really easy and field firmware like updating really easy. So yeah, that's a smart move. Ooh, what does that barcode do? So on the back here, we've got a nicely shielded PSU. as usual, Uni-T probably wouldn't have designed that. You'd subcontract that out to a manufacturer. It looks like probably only the 2 voltages, it's probably only like 12 volts coming out of there. Just got a basic fan over here, no compliant mounting or anything like that. So really basic cost stuff in terms of the power supply here, and nothing on the backboard really. There's just that little 1 micro coax going over to there for higher frequency stuff, and the rest of it's just going over the ribbon cable. So yeah, bare bottom pricing. The earth-in's adequate and everything. So it's all neat and tidy, but no, they haven't gilded the lily anywhere in here. So at a first pass, you're looking at the majority of the BOM cost like being the semiconductors on this board. Once again, this is 500 megahertz stuff, 2.5 gig samples per second. You're going to be paying a premium, a very sweet premium for the DACs on here and like the output amplifiers and stuff like that. They're all going to be premium stuff. You're not going to get something from the Shenzhen market. All right, let's take a look at the board and the BOM cost here. This will be greatly simplified, so please excuse the crudity of the model. Didn't have time to build it to scale or to paint it. So before we get into the main board, let's just have a look. You've seen the outside metalwork as well. We've got the plastic front panel molding as well. We've got the front panel keypad, membrane PCB. We've got the membrane overlay. We've got the LCD screen. We've got all that sort of stuff, and the back and front housings which go into this thing. So there's quite a large bill of materials for this thing. But let's just take a look here. We've got our power supply, of course. This is a 100 watt jobby. It's got 100 VA on the back, so we'll just take that as a ballpark. Very simplistic design here. There's active, if you're wondering where all the active electronics are, they're on the bottom. Sorry, I didn't bother to take that out, but very simple, sparse, large board. But of course, if there's one thing that China do cheap, it's power supply modules. And so, yeah, this is like, I don't know who manufactured this, but it doesn't matter. And we've got a rear panel PCB up here, which is basically just a bunch of B and C connectors and Ethernet over here, and just a ribbon cable going over. We've got a mains input here. We've got just a generic fan. There's nothing special about that. It's not super whiz-bang, low noise jobby or anything like that. So nothing special. Just got a simple cable harness coming out of here. And you can tell this power supply's on the cheaper side because, well, the caps here, we've got JW Co. They're a big Chinese manufacturer, but they're nothing of note. They're nothing like, it's like you may not have ever heard of them before. So, yeah, they're a complete nothing burger. They're not Japanese caps or anything like that. So the power supply is neat and tiny. It's got all the requisite protections and everything else. There's your output filter in there. Incidentally, we've got 17.5 volt power. I thought this would just be a fixed 12 volts, not plus minus 17 volt power. It's got a power kill there. It's got minus 8.5 volts and plus 6 volt power. So obviously that's running all of the digital stuff. So they'd be dropping that down. There's be some mix of 5 volt parts on there, 3.3, and then the FPGA will drop that down even further to your 1 volt, 1.2 volt rails and stuff like that. But that'll be on the main board. Plus minus 17 volts, of course, for the analog sections, and plus 6 volts is just standby for the processor because it's a soft power button jobby, and yeah, nothing fancy. So yeah, I've got a price for that, which I'll show you later. Now, let's go over to the main board over here, and I've removed the metal shielding around here, and there's our FPGA, which we'll take a look at. It's a Kintex 7 here. Main processor over here. We've got our waveform memory. We've got our DACs here, and here I only took off these two heat sinks because these will be identical parts, and you can guarantee that. And this one over here is a different DAC part again. So you can see we've got one channel here, okay, like this, which has got one of the big 14, 16-bit DACs, the 2.5 gig sample per second. We've got a 50 ohm output impedance. Then we've got our switching relays for different levels and stuff. So, and then that is duplicated identically again here, like this. So it's laid out a little bit differently, but trust me, if you go look into the details, all this circuitry here is exactly the same as this up here. So those two channels, channel 1 and channel 2, are identical as you'd expect. And then over here, we've got channel 3, which is shielded, and channel 4, which is not shielded. Once again, absolutely identical. If you want to look at the high-res photos, you go over to my Flickr account. This is not a teardown analysis, really. It's more of a BOM analysis. And you can see that these both of these come from this DAC over here. And you can see that there, like that. Whereas this one has, these two have their own dedicated DAC, 2.5 gig samples per second, channels 3 and 4, because they have lower bandwidth and lower sampling specifications, they're sharing a DAC down here. And as you'll see, curiously, they're a different manufacturer, and these are not what I expected. Just as a little aside, you might be asking, why is there only shielding on 2 of the channels, channel 2 and channel 3? What's so special about them? Why don't channel 1 and channel 3 get shielding? Well, in this particular case, it's a nice cost-cutting measure because Uni-T, the designers, decided that, well, we're not, because this is all low impedance stuff, right? DACs are really low impedance outputs. We've got, you know, like 50 ohm drive, right? Really low impedance driving out of here. So when you talking about something with a low impedance source, then it's really difficult to have external interference, like external, you know, EMI, coming in and disturbing that circuit because it's very low impedance, and whereas all the stuff coming in is very high impedance, so it doesn't really disturb it. So you don't really need any shielding on a low impedance circuit like this as far as external you know, influence comes in. You might need it for if you don't want it to radiate stuff, but that's a different aspect to actually being shielded to protect it from any outside interference. So, but why is channel 2 special? It's because this is low impedance and high voltage swing, when you've got another channel which is right next to this channel is switching, could be a big square wave, boom, 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 you know, plus minus bloody 12 volts or something, right? Then that can easily couple into the channel next to it, right? So you want to shield one channel. So this is not from any external thing, from any external noise from the instrument. It's designed to stop coupling between channels like this. It goes in both ways, like that. Yeah. And of course, likewise, channel 3 is right next to channel 2, so you want to shield that one. But channel 4 over here, well, you want to shield it from channel 3 and maybe channel 2, but you don't need to shield it from channel 1, which is quite a significant distance, physical distance away here. So that's why they can save some cost on the shielding there. So they definitely have thought about cost in this right from at the bare PCB design level. Like, because I don't see any extra like holes in here for the metalwork, right? There's just nothing. It was designed. Look, they actually left the copper off there, right? For these shieldings, you can see the copper being left off. So they actually knew from the get-go that this was just about coupling between channels. So it's not like they you know, built this and then tested it and go, oh, we can leave off this shielding. They knew that from the get-go when they designed the PCB. So definite cost cutting there. And I'll just show you a quick close-up of one of those output sections here, so you can have a squeeze. I've actually got these parts on my spreadsheet. I'll show you later. Japanese relays, Bobby Dazzler, right? So they haven't skimped there. They've got good Japanese relays. But apart from that, yeah, there's not actually a huge cost in this output stage here. And there's just a close-up of the other output stage with the DAC over here. So yeah, neat layout. And I just love all this multi-stage filter in here. Oh, this is just pornographic. It really is. So they really want to filter out those. They would be for the analog relays. We've got an LM337 over here. We've got another jobby there. I don't know if I can't remember if I included that in the spreadsheet, but yeah, these are just, you know, really Joe Blogs are regulators, but they really wanted to filter the absolute crap. They've left out a couple of inductors there, but they decided, oh, I'll keep the caps in, and there's a couple of extra stuff filter in here, missing here. I'm not sure why, but anyway, yeah, they've gone to a lot of trouble to filter those analog rails. And up here, they've got, I love the little modular block, little pro PCB tip. Yeah, add little block sections like that, but extra pro tip, label them, please. Like, they haven't really labeled this. Like, what is the function? Obviously, that's an oscillator with a you know, a PLL hooked on there or something. And this is I believe this is a comparator, because this goes off to the rear panel. It's got like a frequency counter stuff built in, so it's got all that functionality. So yeah, they've just broken that, but you know, not a huge cost in this sort of stuff. Now, if you know anything about semiconductors and pricing, you'll know that the two biggies in this thing, the two costliest parts, are going to be your gigantic big ass FPGA here. It's a Xilinx Kintex 7, that's one of their big daddies, and also the 2.5 gig sample per second DACs in this thing, because these are what, 14, 16-bit jobbies, right? Huge. This here, by the way, that's just a that's the clock gen there. I've included this in the spreadsheet, and also there's the main reference oscillator over there, and that's actually a temperature compensated oscillator, as a digitally temperature compensated oscillator there. So yeah, there's going to be a huge cost. So Xilinx Kintex 7 and XC7K160T for those playing along at home with the extra part numbers, because you can double or triple the price based on what that extra stuff on the end is. So obviously what we've got is a really big, fast Kintex 7 FPGA. I thought this might have been a Xilinx Zinc or something like that, which contains the processor, but that's not the case. This AM3354, it's upside down, so all the electrons are going to fall out. That is the main processor. That's a TI jobby over here. So they've gone for a TI jobby. So on one hand, you've already seen how they tried to like shave cost on like the shielding on some of the output circuitry, but then they don't try and save cost. They use a TI part, and as you'll see, it's reasonably expensive, a TI processor over here instead of one of the Asian sourced ones, which should be, you know, much cheaper. But anyway, yeah, that's separate. And then we've got very fast DDR3 SRAM here, another DDR3 SRAM, but that's coupled into the processor. So these are obviously our waveform memory, and of course, because this is an arbitrary waveform generator, yeah, this has to be really super quick. It has to keep up with the 2.5 gig sample per second DACs over here. So that's why they need a big, grunty, fast and massive FPGA over here, coupled to some fast DDR memory over here. And everything runs on the SD card over here, which is pretty groovy. I like that. Not exactly if you're shaving every cent off your design. You probably don't want to do that, but from just a design flexibility point of view, yeah, that's a winner. And interestingly, I couldn't get any info on this jobby here, and OT8618. I assume it's maybe some sort of flash, which is coupled into the processor over here, but yeah. So what I've done is a BOM Cost spreadsheet here. Again, didn't have time to build it to scale or to paint it. Very rough analysis of what it's going to cost, and I'm pricing everything based on 1,000 quantity here, because that's a nice, you can get that number from the component distributors and stuff like that. And really, they're not making tens of thousands of these things. You go to the Uni-T direct, because Uni-T will sell you this direct from their own website, and they've got stock of like 50 of them, like 50 units. This is not, you know, it's like it's almost $6,000 unit. They're not going to be selling tens of thousands of these things. They're going to be selling like maybe thousands tops. I don't know. If you think I'm wrong, put it in the comments down below. Could be more than that. They could sell tens of thousands, but I doubt it, right? This is a high margin, low quantity product. It's not like manufacturing a $300-400 scope that they're going to sell in massive volume. It's a more niche item. So 1,000 quantity, I think, is really quite decent. So I've put in some various major parts here. Obviously, I'm not going to put in absolutely everything. So this is the processor here. That's that TI jobby. It's a 1 gig ARM Satara microcontroller from TI, and all this pricing is in US dollars, by the way, Yankee Freedom Bucks. So that's actually $11 for that processor, which, you know, it's pretty pricey. And then they've got that part there, which I said I couldn't identify, which I think might be a program flash or whatever. I just put in, I don't know, $2 or whatever. Then here is, of course, the major cost, and we have to guess at this. So that Kintex 7 FPGA, I've put in a price of $260, because if you go and look this up, it's basically double that for a one-off price. Now, of course, you can't get volume pricing on these things unless you specifically go and do a deal with the manufacturer or via one of their distributors who will deal for you. And if you're a good customer, if you're in their good books, you know, you might get substantial discounts. And for most of these pricings, I'm going to use LCSC, which is basically China's equivalent to DigiKey, Mouser, Farnell's, that kind of thing, Element 14. So it's their like catalog distributor, but you can get a lot of Asian sourced components components there. So when you're doing BOM cost analysis like this, it's probably better to use this than DigiKey Mouse, because this is kind of like, you can get like a cheaper Asian pricing often. But of course, there is no second source for these FPGAs. And if you have a look at like DigiKey pricing here, once again, I'm not sure I've got the exact part here, because all those letters and numbers at the end of it like mean something. So, you know, like 750 Yankee bucks one-off price and everything. But of course, you're not going to be paying that in volume, and it depends on the customer relationship you have with the manufacturer or your dealer, you know, official Xilinx dealer and everything else. But anyway, I've gone for like 260 bucks, which is roughly half of the one-off estimate. Now, it could be cheaper than this based on the exact part number, but it's hard to actually search for the exact absolute one based on that. So there could be subtleties in there, and it could change the price quite a lot. But anyway, I've gone for 260 bucks. It's an expensive part, but even if I have got that wrong and you even take 100 bucks off that, then we can see that at the, you know, just take 100 bucks off the final pricing that we look at. But yeah, anyway, it's hard to get a price on that, but it's the most expensive component on the board. And then throw in a couple of DDR3 SRAMs here, you know, a couple of bucks, it all adds up. You've got a flat link LCD driver there. Then you've got a couple of high-speed Peckel comparators in here. They were in that big block that I saw with all the multiple blocks in there. I think they were in there, you know, and they're $2.50. You know, it's not cheap. And then we've got a PHY here. That's for the Ethernet PHY thing. And then we've got I found a low noise op amp there. I don't know. I just put Y. And then I found another relay. There's 25 cents. All adds up. And then that 10 megahertz temperature controlled, temperature compensated crystal oscillator, digitally temperature compensated crystal oscillator. It's $5, for example. And then I've just added on some miscellaneous chips at $10, and the SD card socket and ribbon cables and connectors and fans and heat sinks and stuff like that, right? But we haven't even looked at the output driver yet, which is where the second most expensive part will come in, and that's the 2.5 gig sample per second 14-bit DAC. And this one's interesting because it's not a manufacturer that I've heard of. The part number is CBM 97D39. And this is an Asian manufacturer I'd never heard of. And there's two of those, of course, channel 1 and channel 2, and they're $40 US a pop. And you can actually get that on LCSC. Check it out. They do actually have it here. Digital to analog converters. Oh, yeah, there it is there. And they've got 30 off pricing. So I just actually lowered that, you know, when you're buying 1,000 of these things, or well, in this particular case, 2,000, I just assumed that maybe you might be able to get it for $40. I don't know. I might be undercharging there. But yeah, they actually sell this digital to analog converter. And we can take a look at the data sheet. It's from a company called Corby Microelectronics, and well, who had any clue? So I just assumed that the Corby.com, I just assumed that this would have been a TI or Analog Devices jobby or whatever, you know, one of the biggies, I assume, but no, it's not. It's from this company that specializes in, look, high-speed op-amps. They do a whole bunch of stuff. They do analog and stuff like that, but they do DACs, high-speed, DAC converters, quadrature ones, precision D2As, DDSs, and stuff like that. So, Corby. There you go. I love doing these teardowns. You learn something new every day. And we can download the data sheet for this jobby, and here it is, 14-bit, 2.5 gig sample per second DAC. 14 bits, direct RF synthesis, blah, blah, blah. DC to 1.25 gig in baseband, to 3 gig in mix mode, LVDS interface. It's got DDR clock-in and programmable output currents and broadband communications, military, radar, activation SIM, test the system, equipment, instruments, and automated test. And yeah, who knew? I was very surprised to find this Asian source DAC in here. Unbelievable. And channels 3 and 4, they have saved a bit of cost here by not having those high sample rate DACs there. So this is an Analog Devices jobby. It's an AD9122, but it's still $10, but at least you share, you know, one of those between channel 3 and channel 4. And as you can see, we can get that from LCSC, 100 of quantity, $9. And once again, it depends on like the grade you get or whatever here. So yeah, but we can download the data sheet for that. Oh, thanks, Chinese. Anyway, you get the point. It's a 1.2 gig 16-bit DAC, so you do get the greater resolution on channels 3 and 4 there. Then we've got an analog devices clock gen here. That's 2.5 gigahertz. That's our sample clock. That's $7, so that's not cheap. And then we've got all those output signal relays as well. So there's actually 20 of those. There's 20 of them, because yeah, there's a lot of those, and at 50 cents each, there's another $10, right, for those Japanese relays. Then there's actually an analog devices FET op amp in there, in each output channel. So there's 4 of those. They're $1.80 each. And I said, well, why do they need such an expensive op amp? I don't know, low offset or something. Looks like it's an 80 microvolt 20 megahertz part here. Precision, very low noise. Yeah, so you're going to pay, you know, a premium for that. So they got one of those in the output channel for doing all the offsetty stuff. But you've got to have all these grunty drivers. Remember, you can't just drive from the DAC directly to your 50 ohm output. So you need these 900 megahertz current feedback amps. And there's 12 of these. These are THS 3491s. There's 12 of those at $7 a pop. $7 a pop. That's actually technically more cost than the DACs. So they've spent more on the output drivers, potentially more on the output drivers than they have on the DACs. Unbelievable. And check it out. These are LCSC pricing at 1,000 of quantity here. Like $7. Sure, they'd be ordering like tens of thousands because you need a whole bunch of these to make 1,000 units all up. And you can see how this can go anywhere from $7 up to $18. Right? $18 for exactly the same part, but it's just got those different letters on the end because it's a different grade. So like you can have a look at the data sheet. They often don't give you the English one. Sorry, I won't go bother looking for the English one. But yeah, all these different grade parts. Yeah, but you can often get parts like this specified in various speed and offset grades and all sorts of things. And you can pay a premium depending on which actual part that you're actually getting. But it could also be like a package thing. If it's in some rare package that you decide to design into your board, then, well, you know, you could pay like double for it or something like that for some weird ass package. So beware. So I'm not going to look into the details, but like, yeah, it's the same part number, just with different letteries on the end. So, and they're both got I, so that indicates industrial temperature range instead of C, commercial. That's common that you'll see. You'll see a C in the part number, or like after the part number, or an I. That's just a different temperature range thing, obviously, but they're expensive parts. More expensive than the DAC. Who would have thought? So these are actually these parts here, right? 1, 2, 3, 4. Right? There's 4 per channel. So like this adds up. And they even use them on the lower frequency channels 3 and 4 over here. So maybe they are getting them cheaper than that, but you know, an LCSC is a pretty cheap supplier, but they might be, you know, because they're probably ordering like tens of thousands of these. So yeah, they're probably getting them directly from the manufacturer, but yeah, there's 4 of those per channel. Pricey little buggers. And then another pricey part is an LMH 65552 here. Need 4 of those, so there's 1 of those per channel, and they're like $7 a pop as well. So yeah, $28 total. Damn, that adds up. So there you go, 100 of quantity, $7.60 there, and we can. It's a single 1.5 gig fully differential amplifier here. So it's basically a very high speed single-ended to differential driver. So you've got to have one of those, unfortunately. So if we actually sum up just that output stage there, you can see that there's $237. $237 just the output stage with the DACs and the drivers and whatnot. Unbelievable. Then we've got various power supply stuff that's on the main board. You could go to town with this. So yeah, I won't go through details, but like they've got linear technology parts in there, so they haven't tried to skimp, even though they're like $2. I put big letter difference in because I found a big price differentiation in that part. You can go look it up for yourself and stuff like that. Couple of bucks for passage. Anyway, like, yeah, doesn't matter. I didn't want to spend any more time on that. But let's get down into some more stuff here. We've got the mains power supply unit. So that 100 watt brick power supply, I put in a nominal 10 Yankee bucks here. I don't know. Whatever, you might get it a bit under that, you might get it a bit over, depending, but you know, I just put in around 10. I've just rounded off quite a few of these numbers. Metal work here. Now, I did actually put quite a few of these things into Grok to give me a price breakdown rather than do extensive research myself. I just got a summary from Grok, so I'll put up some summary overlays here, but I did some stuff on the metal work for the amount of, like, for the sizes and everything, and the, you know, the thickness and the gauges and the fold in and all the rest of it. I think I got about 20 bucks, something like that for the metalwork. I don't know. Mechanical engineers, leave it down below. Is that an order of magnitude out? Nah, it's only a couple of bucks, Dave. Or no, well, that's a bit cheap, Dave. You know, all that metalwork costs money, didn't you know? And then we've got that output PCB with the actual connectors and the ribbon cable going over. It's just BNC cables. There's no circuitry on that, so you just put $5. And then you got the front panel plastics. I forgot the rear panel plastics, so it could actually be double that. So I might actually put in 2 there. There you go. So yeah, you got the front panel plastic moldings and the rear panel. Of course, you'll have NRE tooling on that. I haven't actually put any NRE tooling for that, but I think that's included in the Grok pricing. So I got some Grok pricing for like an equivalent size kind of thing here. So yeah, the plastics, you know, don't come cheap. The LCD, it's a 1280 by 800 touchscreen LCD, doesn't come cheap. So I did some Grok pricing on that and was like, yeah, 35 bucks. It's not, you know, maybe you can get it cheaper. Something like that. Maybe not. I don't know. Leave it in the comments. The keypad PCB and the membrane overlay sheet and everything, not hugely expensive, so I whacked in $5. And then every unit, of course, must be calibrated and tested. And so there's labor cost for that. I've just put in $10, round figure, something like that. I don't know. PCB assembly. You know, this is quite a big board, right? This is a large size board with lots of complex, fine pitch, stuff on it, big BGAs and other things. So it's not cheap to assemble this, and there's a ton of passive parts on here. Okay, so I think I included like a nominal cost per component build out of China or whatever. So it's $10. I don't know. Leave it in the comments. Is it more than that? Is it less than that? It could easily be more than that. Like, you're not going to get it for a couple of bucks. When you get your tiny little widget assembled in China at JLC or whoever, you know, PCB wafer, like this super cheap as chips, you got to remember, this isn't like a huge serious production board with thousands and thousands of parts on it. So yeah, it's time consuming, and you've got to load up multiple machines because you can't fit all the reels on the one machine, so it's got to pass through multiple machines to get all the assembly, and it's like, yeah. Okay, so $10 could actually be cheap there. The bare PCB, this is at least a 6-layer job. It could be 8 layers because you've got to fan out the big FPGA and the other stuff. I just cheated and got Grok to give me a breakdown on that rather than go to the bare board manufacturers and do that. $10, you know. So I'm just like ballparking these kind of costs. Now, of course, you got NRE. So we have to include some NRE, which is non-recurring engineering, which is the one-off costs that it can include tooling, but it also includes the design of this thing. You've got to pay engineers for like a year or a couple of years to actually develop this thing. And so once again, I've assumed that they've got like 10 employees working on this. You know, you're going to have an FPGA person, you're going to have a software person or two, you're going to have, you know, a PCB layout person, you know, you're going to have the designer of the who's designing all the schematics, you're going to have a manufacturing engineer, and right, there's, you know, I've got at least 10 employees, right, working on this sucker for a year. And I actually got, once again, Grok to give me a base ballpark of what a development salary for an engineer in China is actually worth, and it's actually $50,000 a year. So multiply by 10 employees, you're looking at a total cost of $500,000 for the development of this thing. This doesn't include management or other company overhead at all. So it could be, you know, it's at least 500,000 Yankee bucks to design this thing, just in terms of like labor and company overhead. It could be $1 million more, could be a couple of $1 million. Leave it in the comments what your best guess is. That if you've worked in the Chinese company, for example, and you know what the exact costs are, let us know. I've assumed that we're going to manufacture, I know I've done pricing for 1,000 units, but I assume that we're going to make 5,000 units. That's just a decent number to work from. So you've got to what's called amortize that MRE cost. That means basically spread across. Amortize means like take that one-off cost and spread it across each individual unit. So over 5,000 units, that $500,000 works out to $100 per unit. Because you have to pay for the development. The company's got to make their money back, right? So there's $100, 100 Yankee bucks per unit just on NRE. And then I've got test jigs down here. You could easily like spend 50 grand on some one-off test jigs and stuff like that. So you amortize that over the 5,000 units. There's $10 a unit just for you to, that's where I come from the test engineering industry. It's nothing to spend like 50 grand on an automated production tester. I've spent like 10 times that on automated production testing equipment and stuff like that. So yeah, and that's just not hardware, but it also includes software and all sorts of other things as well. So we've got a total here, oh look at that, I've rounded out pretty well, $800 for the BOM cost. So there you go. Like, once again, leave it in the comments down below if you think that's double what it should be, or if that's half what you think it should be, because it might be a lot more, something like that. But that adds up to, there's lots of little stuff missing and stuff like that, but they kind of come out in the wash. So even if I'm out on like that FPGA, I'm, assuming double or triple it, like, you're well over $500-600. You're into your $800, maybe even $1,000 base cost to actually, all things considered, to design, develop, test, and assemble each one of these units. Then on top of that, you've got like packaging as well. You've got to package it nicely. You've got to include all the accessories. didn't even think about those. The mains cable, any test cables or whatever comes with it, manuals and things like that, they all have to be included. And then you've got to, of course, have dealers as well. So you've got to have quite a margin in there for the dealers. The dealers aren't going to be making 5 or 10% on this instrument, right? They're going to make significantly more than that. I'm not sure what the Uni-T dealer margins are, but no one's going to be working for 5%. T equipment here, right? They're selling it for the $5,800. They're not going to be making like 5% on this thing. I'm sure they're going to be making it, quite a reasonable margin on these products. And of course, Uni-T also sell it direct. I think you can buy it directly from their website. But the margin for the dealer has got to be in there as well. And then you've got all the support costs as well, because you've got to have support engineers to support this thing. And then, and then you might have failure rates in there. So you might have, a scrappage percentage in there. They probably wouldn't scrap entire boards at this sort of price level. You would if you're manufacturing, say, a multimeter and the bare board costs like $50 in parts to assemble. Well, you're probably not going to be, if one of those fails your automated testing, you're probably not going to troubleshoot or repair that. But an expensive board like this at like $500 or $800 for a board, well, bare board's a bit cheap in that, but at many hundreds of dollars, it might be worth half hour or an hour of someone's time to go in there and figure out what the issue is. Like, you wouldn't just scrap boards, but anyway, you got to factor all that sort of stuff into your cost analysis of this thing. Then you've got to have the margin in there for the company to make a profit, of course, obviously. So that's what that 2.5 multiplier cost multiplier is, which I had in my analysis video, which you should go and watch. But bigger companies have different margins and stuff like that. So yeah, we don't know exactly what only Uni-T would know exactly what the manufacturing cost for this thing is, but you can see why, if it's $800, like you can see why it's going to cost like $3,000, $4,000, $5,000, $6,000, something like that at the final retail price. You've got to have room to, of course, have specials and lower, lower prices and stuff like that if it's not selling. So, you're not going to start selling the thing at a loss. So you can see why, yeah, before I started this, I thought, oh yeah, it's got to at least cost $500 to $1,000, and that's what popped down in my spreadsheet. It was that like $800. Don't know if that's accurate, but it's not going to be $80 and it's not going to be $2,000. So yeah, I think somewhere $1,000 is, you know, a decent cost for this thing. It may even be significantly more than, maybe over $1,000. We don't know, but yeah, because they don't make a huge lot of this. Anyway, oh, it's longer than I thought. Hope you found that interesting, and if you did, please give it a big thumbs up. As always, you can discuss down below in the comments, or where everyone talks about test equipment over on the EEVblog forum, biggest test equipment section on the interwebs, because everyone loves their test gear over there. But if you have a better insight, because I've been out of the production game for quite some time, if you've got better, more precise insight for stuff like this, or things that I missed, I didn't cover everything. I just slapped together something, and I think I'm in the ballpark. What do you reckon? Let me know. And don't forget to check out the EEVblog.store for all of my merch, because the manufacturers sell these at a free on board cost, a FOB cost to me, and I make my margin, and that's where I make a good majority of the money that keeps me in business here, is the EEVblog.store. So check it out. And yeah, it's all about margins, which is why you don't see me selling like a, you know, a $20 Uni-T multimeter, because the margins, the smaller you get, the smaller those margins, the lower cost you get, the smaller those final retail margins get. So yeah, so you don't see me selling like a cheaper, lower end stuff, because just, you know, the manufacturer margins aren't there, especially in the higher volume cutthroat business. But yeah, for more expensive stuff like this, yeah, there's going to be quite some margin there. But yeah, just because it's made in China, you can't churn out something like this for $50. It just doesn't work, because those semiconductors, they cost a lot of money, and all the rest of the rigmarole that goes into this. Not to mention the development of such a complex bit of kit. You know, like your modern oscilloscopes, and even, this is just a function gen, but the amount of software and engineering development that goes into this is quite huge. So yeah, hats off to companies who design the advanced products we take for granted these days, even if they are pretty expensive, at least for a function gen. But hey, this one's cheap. You can pay an order of magnitude more than that for a function gen. Catch you next time.